Let's see a couple of proofs by using the epsilon definitions. These are not important in this course, but they are used in mathematics courses, for example in real analysis. So we saw that the definition for a sequence to have a limit is that for every positive epsilon we should have some n epsilon which belongs to the natural numbers in such a way that starting from that index the ans will be at most epsilon away from the limit capital A. So the definition means that our sequence can at first do anything, but then after the limit index it has to stay in the tube. Let's prove that if we have a limit, then our sequence is bounded. If we choose epsilon to be 1, we will find some limit index so that for n larger than this limit index, we will have the inequality which shows that this is true. Here we don't know what kind of number capital A is, but still we can conclude that the absolute values of an are at most this number. Namely, we can start from this, we can both add and subtract capital A, and then we can use the triangle inequality to these two terms here, and the second term is less than 1, so we will obtain this inequality for these values of n. We obtained this useful identity for n's larger than n epsilon. And let's take the maximum of these absolute values where n does not satisfy our condition. Now this number capital M defined in this way is larger than 0. Now we obtain that ans are less than m for all n, so the sequence is truly a bounded sequence. Let's prove this theorem. Let's make a proof with epsilon. We need to get this expression to be less than epsilon. The trick is to subtract and to add the same term. Now we can take some common factors. Then we can use the triangle inequality. Because bn's converge to capital B, the sequence bn is bounded, so it is at most some constant m. This holds for all n. Because the bn's converge to B, we can make this kind of inequality. Here we put in addition to a plus 1 because we might have that capital A is 0. In the same way, let's see, an minus capital A is at most epsilon over 2 times m. Well, let's add a plus 1 there also, no problem. When n is large enough, let's say larger than nm. So when n satisfies these two conditions, the product of these two terms will be at most epsilon over 2, and the product of these two terms will be at most epsilon over 2. Well, we can say even we should have here maybe a strict inequality. Then we can have here a strict inequality. Like this. So the expression is at most epsilon when n is larger than some limiting index. So our proof is complete. These proofs are not important, but maybe in some future mathematics course you will need such proofs. So here were a couple of examples about this.